Hi everyone, we are Group 18, Junleong, Hongjing, Jiaqing, and me, Junsheng. We're gonna discuss about simulation of multi-stage amplifier. This is the introduction and problem statement which require us to design and simulate an amplifier system according to the appendix.
I will explain the design and simulation setup for our multi-stage amplifier. As shown in the block diagram, our 10 mW AC input signal enters step 1, a common source MOSFET amplifier. The signal then enter into step 2, which is common emitter BJT amplifier, then finally reach the 20 kilo ohms output load. Moving to our LC Spice schematic diagram, so this is our physical layout. Both amplifier states share a 15 watt DC power supply and are properly separated by 10 microfarad coupling capacitor to isolate their DC biasing. To ensure our simulations match the specific project requirements, we had to add custom Spice corrective. Configure the MOSFET modulus Kp parameter to 2m over V square since the required K value is 1 and the V3 is equal to 1V, and we set the BJT's beta exactly to 350. We configured two separate simulations. We use a DC operating point command to verify our steady state biasing and a 5 millisecond transient analysis to capture multiple circuits of our AC waveform. This step fully prepare our circuit for the final calculations.
First, we run an LT-SPICE operating point simulation to capture the raw knob voltage and divide currents using a step 1 drain voltage of 6.516 volts and a step 2 base voltage of 1.601 volts. Next, we mathematically validate this value using hand calculation, applying KVL and the MOSFET square law for step 1, alongside Terbinon theorem and active region BJT loops for step 2. Comparing the two, our percentage error are exceptionally low, mostly under 5%. The outlier in VDS is simply due to a small numerical variance over a tiny voltage, confirming our design accuracy. Finally, we verified DC isolation. Coupling capacitor C2 brought a 4.915 volts drop with a near zero vector amplifier leakage current, proving it acts like a perfect open circuit to keep both Q point perfectly stable.
So now let's move to the AC transient simulation. After running the simulation, we first place the voltage probe at the input node Vin, which is located after the signal resistance. The green waveform represents the input signal. Next, we place the voltage probe at the output node Vout across the load resistance. The red waveform represents the output signal. When both signals are displayed on the same graph, we can clearly see that the output signal is amplified compared with the input signal. From the waveform, the input amplitude is approximately 10 mV, while the output amplitude is approximately 63.41 mV. Both waveforms have the same frequency of 1 kHz. The output is in phase with the input because the MOSFET and BJT stage each introduce a 180-degree phase inversion. Therefore, the two inversions produce an overall phase shift of approximately 360 degrees, which is equivalent to 0. Using the amplitude value, the voltage gain is calculated as Vout over Vin. So we can get the voltage gain is 6.34, which is 16 in decibel. In short, the output remains sinusoidal with no visible clipping or distortion, showing that both transistors are operating in their amplification region.
I will be explaining the AC voltage gain calculations for our multi-stage amplifier.
For the first step, our common source MOSFET, the voltage gain depends on its shunt conductance and its total AC load. The load is the drain resistor is in parallel with the input impedance of the second stage. Using our calculated DC operating point, we found that GM1 to be 1.22 mA per V, giving us a drain 1 gain of negative 3.51. Moving to the second stage, the common emitter BJT. Notice that the emitter resistor is unbypassed, which provides stability. The gain here is determined by the BJT beta, the parallel output load, and the base resistance combined with the reflected emitter resistance. Plugging in our value, we get a stage 2 gain. Finally, the overall system voltage gain is simply the product of individual stage gains. Multiplying two values gives us a total gain of 6.7 or 16.52 dB. Because both stages inverted the signal, the negative sign cancels out, meaning our final output is perfectly in phase with the input.
In conclusion, according to what we see just now, there is a difference of about 2.46%, which is indicating close agreement between the theoretical and simulated result. This small difference caused by the simplified assumption in the theoretical analysis, such as ideal transistor behavior and negligible internal parameter, while LT-SPICE consider the transistor model, loading effect, and circuit component interaction. So overall, the simulation validates that the theoretical analysis and confirm that the amplifier operates correctly within its linear amplification region. That's all for our video. Thank you.